This podcast talks about atomic orbitals and how they fit into the quantum mechanical model of the atom. So the Schrödinger equation describes how an electron's matter and wave properties and fit in three-dimensional space, and how they are arranged around the nucleus. The equation is written energy equals h psi, and these are definitely different symbols than we're used to seeing. E stands for energy. This guy here is a Greek symbol psi, which stands for a wave function. It is not a simple number. It's a complicated, sometimes very complicated equation. And the H, which is often written in as a really big, fancy H, stands for Hamiltonian operator, which is a set of directions for what to do with the wave function. It's definitely not a simple variable here. We're not going to solve the Schrödinger equation. I just think it's important to see it. It involves math like matrices and linear algebra and pretty complicated math that you don't usually get to until your first or second year of college. Each solution to the equation, which is really what we're going to care about, is called an atomic orbital. And what it tells you is, where are you likely to find an electron around the nucleus? When you square the wave function, psi squared, we get what we call a probability density, which means that for every given energy level, we can show the probability as a picture that looks sort of like this, where if there are more dots, it means that we are more likely to find an electron there. So when we draw the orbitals, and we draw this orbital as kind of like, looks like a basketball, but it isn't really a solid sphere. It actually is giving you the probability, and it's not the same all the way through. So an atomic orbital can be specified by quantum numbers, 3 quantum numbers for the orbital, one for size, one for shape, and one for orientation. These 3 quantum numbers have a hierarchical relationship. So the first one will specify what the second one can be, and the second one will specify what the third one can be. And we're going to talk about them each individually. The first quantum number, which we call the principal quantum number, n, it shows energy level and size. And the allowed values for n, it's always positive, can't be 0, and it's going to be whole numbers, 1, 2, 3, etc. In theory, it can go all the way up to infinity. We don't get that high because we run out of electrons. But it could. But it does have to be a whole number. It cannot be a decimal. The next quantum number is the angular momentum quantum number, which has the symbol L. It's usually written as a scripty L. L shows sublevel, or shape, and the allowed values for L depend on n. So it can go from 0 up to n minus 1. The third orbital quantum number is the magnetic quantum number. And it is m sub L. That's supposed to be a little l there. It shows orientation, and its values depend on L. So m sub L can be from L up to 0 to plus L. So how do we use these guys? This chart, which comes from your textbook, is an overview of the hierarchy of quantum numbers for atomic orbitals. So here you've got n, which is the principal quantum number, and it has to be a positive integer. It can be 1 or 2, or this chart goes up to 3. Okay, so we're going to give all the possibilities for n equals 1, 2, and 3. Angular momentum L goes from 0 up to n minus 1. So if n equals 1, L goes from 0 to 0, which means it has to be 0. The important thing is there's one possible value for it. That's what we really care about. If n equals 2, then L can go from 0 up to 1, which means there are 2 sublevels in the second energy level. If n equals 3, L can have the values of 0 or 1 or 2, which means in the third energy level there are 1, 2, 3 sublevels. All right, the third quantum number, which is the magnetic ML, which tells us orientation, can go from L up to 0 to plus L. So if L is 0, it can go from 0 to 0 to 0, which means it has to be 0, which means there's only one orientation. For the second energy level, L can be 0 or 1. If L is 0, ML is 0, one orientation. However, if L equals 1, then ML can be -1 up to 0 to +1, which means it has 3 orientations, or 3 orbitals, 3 places to put electrons. Third energy level, L equals 0, ML equals 0. L equals 1, ML -1, 0, or +1, which means 3 orbitals. L equals 2, then ML can be -2, -1, 0, +1, or +2, which means there are 5 orbitals in the sublevel, 5 places to put electrons. So what we're going to do here is figure out what the values are of the angular momentum and the magnetic quantum numbers for n equals 4. So we are going to do everything for the 4th energy level. Shut off your video and try to do the diagram and then turn it back on and check and see how you did. Okay, to summarize this, n equals 4, so there are 4 sublevels. L equals 0, 1, 2, and 3. L equals 0, ML equals 0, which means I have 1 orbital in that sublevel. L equals 1, I have 3 orbitals. L equals 2, I have -2, -1, 0, 1, and 2, which is 5 orbitals. So far we are exactly the same as the third energy level, but now we add the 4th sublevel. L equals 3, ML is -3, -2, -1, 0, +1, +2, and +3, which means that there are 7 orbitals in this sublevel. So what I've done down here is just talk about how the ML, or the magnetic quantum number, tells you the number of orbitals that you have. And remember that orbitals are places to put electrons. What do these orbitals look like, the shapes? For the first one, L equals 0, so it has 1 orientation, which means it is symmetrical in all directions. 1 orbital, and it can hold 2 electrons. And we'll go into why, but for now, each orbital can hold a maximum of 2 electrons, and we'll give the rule for why later. Okay, for the next L, we call this the p orbital, and L equals 1. So ML is -1, 0, +1, which means there are 3 orientations, or 3 orbitals. Each one holds 2 electrons, so that can hold a maximum of 6 electrons. Next sublevel, L equals 2, So ml equals -2 up through +2, which is 5. 5 orbitals, each one can hold 2 electrons, so it can hold a maximum 10 electrons. Once we get past this one to higher L values, we really stop drawing them because they get really complicated, and you don't have to be able to draw them. You just have to know how many of them there are going to be.